So in this video, we want to take a look at an example. Living alone? In the year 2000, 58% of females aged 15 and older lived alone, according to the U.S. Census Bureau. A sociologist tests whether this percentage is different today by conducting a random sample of 500 females aged 15 and older and finds that 285 are living alone. Is there sufficient evidence at the alpha equals 0.1 level of significance to conclude that the proportion has changed since 2000? Well, so we want to conduct a hypothesis test. I'm going to start this time by writing down what the null and alternative hypothesis would be, and then we'll check our conditions and go from there. So this is a hypothesis test regarding a proportion, and so in 2000, the proportion of females that lived alone was 58%, and this sociologist wants to know if it's different today. So our null hypothesis is going to be that the proportion of females that live alone is 58%, or 0.58, and our alternative hypothesis is going to have the p in the 0.58. We want to know, is it different? So different means not equals. So it's not really saying, is it greater than, is it less than? We're just wanting to know, is it different? So that's going to make this a two-tailed test. They're also telling us that we're supposed to use alpha equals 0.1, which is a pretty big level of significance, 0.1, but that's because the seriousness of making a type 1 error would not be deadly or anything like that. So it wouldn't be a serious consequence if we make a type 1 error. So let's check our conditions. So if we check our conditions, well, we need to know that we have randomness. Well, it says that the sociologist tested whether the percentage is different today by conducting a random sample of 500 females, so we meet randomness. We need to check is n times p naught times 1 minus p naught 10 or bigger. Well, our p naught is 0.58 and our sample size is 500. So if we take 500 times 0.58 times 1 minus 0.58, so we have 1 minus 0.58. Well, 500 times 0.58 times 1 minus 0.58 is 0.42, and that is 121.8, which is certainly bigger than 10, so we meet that condition. The third condition is that we have to have independence, and so again, the way that we determine that generally is that the sample size has to be less than 5% of the population. Well, we have 500 females as our sample size. That's certainly less than 5% of the population of females, so we meet that condition. So we have randomness, n times p times 1 minus, p is 10 or bigger, and we have independence. So our conditions are met. So we're able to conduct our test. And so again, our question is there significant evidence at the alpha equals 0.1 level of significance to conclude that the proportion has changed? Is it now different from 58%? So if I'm going to use the classical approach, then I need to draw my normal distribution, and I need to figure out my critical value or critical values. Now in this particular case, we're dealing with a two-tailed test. I know that because my alternative hypothesis is not equal to. So for a two-tailed test, I split alpha between the two tails. So I'm going to take the 0.1 and divide by 2. 0.1 divided by 2 is 0.05. So the area over here is 0.05 and the area over here is 0.05. Sort of like what happened when we were doing confidence intervals. So I need to figure out what these two critical values are. They'll be the same value except this one will be negative, this one will be positive. So how can I figure out what that critical value is? I can use my inverse norm command on the calculator, which I'm going to use. I could use the standard normal table from the back of the book, or I could use the normal calculator in StatCrunch. So I'm going to use the inverse norm command. The area is 0.05. and that is going to be the area in the left tail if I'm going to find this one. And so that is negative 1.645. This value is negative 1.645. By symmetry, this value is positive 1.645. So I have my figure drawn with the critical regions drawn. Next, I need to calculate Z naught, my test statistic. But to calculate that, I need to know what p hat is. Well, p hat was 285 out of 500. 285 out of 500, that is 0.57. That's 57%. So that is different from the 58%, but the question is that statistically significant? Does that indicate that the 58% is no longer true, or is that perhaps just because of variability in samples? Well, I need to change that to a test statistic, Z naught. And so again, the formula for that is that we're going to take p hat minus the p from the null hypothesis divided by the square root of the p from the null hypothesis times 1 minus the p from the null hypothesis all over the sample size. Well, so that's going to be 0.57 minus 0.58. Again, that's from the null hypothesis, divided by the square root of 0.58 from the null hypothesis times 1 minus 0.58 from the null hypothesis. And that's over 500 because that was the sample size. So if I do this calculation, parenthesis, 0.57 minus 0.58, close parenthesis, divided by the square root of 0.58 times 1 minus 0.58, which is 0.42, divided by the sample size, which is 500, and so I get negative 0.453. So this is about negative 0.453. So looking at my picture here, negative 0.453 would be maybe around in here, not to the left of negative 1.645, not to the right of positive 1.645. So because it's in between, it's not out here in the unusual area. That tells us do not reject the null hypothesis. So we are not going to reject the null hypothesis. Now, if I want to use the p-value approach, I do everything the same except I don't need to draw this picture. The picture's there for the classical approach. So I calculate my test statistic Z naught. I figure out that it's negative 0.453. And so for the p-value, I'm going to find negative 0.453, and I'm going to find the area to the left of that. But because this is a two-tailed test, I'm also going to find positive 0.453 and find the area to the right of that. And so the total area in those two tails will be the p-value. Well, how do I find those areas? Well, for example, I could find this area to the right of 0.453, and then the area to the left of negative 0.453 is going to be the same thing by symmetry, and so I can use that to figure out what the p-value is. So I'm going to use my normal CDF command, although I could use the standard normal distribution or I could use the normal calculator in StatCrunch just as well. So again, my value is 0.453, so 0.453 to a big positive number, and so that is 0.3253 approximately. So this area is 0.3253, which by symmetry means this is the same. So if I take 0.3253 plus 0.3253, or times 2, that gives me 0.6506. So the p-value is 0.6506 approximately. Now, because 0.6506 is bigger than 0.1, so because 0.6506 is greater than 0.1, we do not reject the null hypothesis. So we do not reject the null hypothesis. So whether we use the classical approach or the p-value approach, either way we came up with the same conclusion: do not reject the null hypothesis. So what does that mean? Well, as far as this problem goes, is there sufficient evidence at alpha equals 0.1 level of significance to conclude that the proportion has changed? So the answer to that question is no. There is not significant evidence to make that conclusion. So no, it appears that the proportion of females who live alone is still 58%. We were not able to determine that it's now different. Our evidence supports that it's still 58%. Now we have seen that for all of our hypothesis tests, we have two approaches. We can use the classical approach or we can use the p-value approach. Now, when we have a two-tailed test, as we do in this particular example, we actually have a third approach that we could use as well. And so I want to discuss that next. So two-tailed hypothesis testing using confidence intervals. When testing H0, P equals P0 versus H1, P does not equal P0, if a 1 minus alpha times 100% confidence interval contains P0, do not reject the null hypothesis. However, if the confidence interval does not contain P0, conclude that P does not equal P0 at the level of significance alpha. So I want to take a look again at our example about the percentage of females who live alone. So could I use a confidence interval approach to test this as well? So we've seen the classical approach, we've seen the p-value approach. So if I want to use the confidence interval approach, and I'm going to write that in right here, so the confidence interval approach. So what I'm going to do is I'm going to find a 1 minus alpha times 100% confidence interval. So if I do 1 minus 0.1 times 100, well, 1 minus 0.1 is 0.9, and 0.9 times 100 is 90%. So I'm going to find a 90% confidence interval, and if our 0.58, if that is inside the confidence interval, then we do not reject the null hypothesis. But if this 58% is outside of the confidence interval, then we're going to reject the null hypothesis. So that is the confidence interval approach. Now I'm going to use technology to find the confidence interval rather than doing it by hand. So I'm going to use the calculator. And so if you'll remember, we go to Stat and Tests, and we use a 1 proportion Z interval, which is option A on my calculator. So when I go there, I get a window such as this. So I need to enter the value of X, which was 285, and the value of N, which is 500. And I need to enter the confidence level, which in this case is going to be a 90% confidence interval, again, because that's 1 minus alpha times 100. So if I calculate, I get a confidence interval of 0.53358 to 0.60642. So my 90% confidence interval is 0.53358 to 0.60642. Now again, our approach is, if our value from the null hypothesis is inside the confidence interval, then do not reject the null hypothesis. But on the other hand, if our value from the null hypothesis is not inside a confidence interval, then we do reject the null hypothesis. Well, 0.58 is inside this confidence interval. 0.58 is between the 0.53358 and the 0.60642. So we're again going to conclude, do not reject the null hypothesis. So just like we did with the classical approach, just like we did with the p-value approach, we got the same conclusion with the confidence interval approach. But again, say if this had been, say, 52% in the past, then 52% is not inside that confidence interval, and we would reject the null hypothesis if that had been the case. So as a general rule, we're going to have two approaches, either the classical approach or the p-value approach. But if we have a two-tailed test, then we could also use the confidence interval approach. Now in the next video, we're going to do the exact same three examples we've seen already, but we're going to use technology to conduct the hypothesis tests.